Last time we designed a current regulator using an LM317 voltage regulator IC and current regulator using the combination of simple discrete components. Welcome guys, this is Foolish Engineer. This time we are going to design another current regulator using a transistor and an operational amplifier. So let's go for a ride. The very first thing we need to ask is, what is a constant current regulator? Well, any source which provides constant current irrespective of any change in output load or input voltage is known as constant current regulator. Let's see the basics of current and voltage. When we connect a normal voltage source, let's say a battery, to a resistor, then the current flowing through a resistor will be the division between voltage applied to it and its resistance. Well, this is nothing but the basic Ohm's law, right? So, with this logic, the constant current regulator changes its own resistance in order to give the constant output current, which may result in changing output voltage to pump the current in the load. So, when the load current is supposed to be increased, the regulator decreases its resistance, and when the load current is supposed to be decreased, the regulator increases its resistance. But why do we need a constant current regulator?
Wait a minute!
Well, the current regulator are very useful for driving the strings of LEDs. And it is also useful for capacitor charging circuits which we need accurate timing. So let's see how we can design a current regulator. You know what? A transistor can provide a regulated supply of current. We can use BJT or MOSFET depending upon the current and voltage requirement. So we can add a load to the transistor. We can bias a BJT to its base and a MOSFET to its gate. For now, we'll consider a BJT. Well, the regulators have internal feedback loops, and that's how every regulator provides constant voltage or current for any input voltage fluctuation. So to get that stability, we need to provide some feedback to any discrete circuit which will give the regulated supply. So we need to bias the BJT such that it gives constant current. There are multiple ways to add a feedback path to this transistor. One of the most efficient ways to get very precise current regulation is by adding an OpAmp. That's right, this little triangular thing. We can bias a transistor in many ways. In the earlier videos, we did that with the Zener diode, transistor, and TL431. If you haven't seen yet, you can watch those videos by clicking on this card above. Please do it, they're awesome. We can use an operational amplifier, and this is the circuit diagram. If you compare this with the previous circuits, we replace the whole feedback path. The R1 is connected to the output of the OpAmp to limit the current. R2 is the current sensing resistor. R3 is the current limiting resistor for the Zener diode. Well, if you don't use this resistor, it will just damage itself when it starts conducting. One OpAmp and D1 is the Zener diode, which produces constant reference voltage to the OpAmp. And finally, load is connected between the collector of the transistor and power supply. Here, OpAmp is acting as a comparator. The feedback loop of this OpAmp adjusts its output so that its inverting terminal matches the non-inverting input. The voltage drop across R2 should be proportional to the Zener voltage of the Zener diode. Let's see the working of this circuit. When the supply is connected, the current flows through R3. As the positive terminal of the OpAmp is higher than the negative terminal, The output of the op-amp gives logic high output. This logic high is basically the VCC which is provided to this op-amp. So the output of the op-amp is high and current flows to R1, which turns on the transistor Q1. So the current starts flowing to this branch. Well, as soon as voltage drop across this R2 goes beyond the Zener voltage, that is the reference of the op-amp, the voltage at the negative terminal becomes greater than the positive terminal. So the output voltage of the op-amp will shift to the VEE, which in our case is connected to the ground. So the output voltage of the op-amp will be 0 and the transistor Q1 turns off. Due to this, current starts decreasing through the load and eventually voltage drop across R2 decreases. Again, positive terminal becomes higher than negative terminal, so it turns on the MOSFET right away. This cycle repeats, which gives us negative feedback to get the constant current output at the load side. We can set the current of the circuit using this formula, where Vref is the reference voltage, which will be the Zener voltage, and R2 is the value of resistance R2. Well, the working of the circuit was not that hard, and we can design this current regulator easily. Let's see an example. The output current required from this circuit is, let's say, 50 mA. The input voltage will be around 14 volts. And our load is an LED, which has 4 drop voltage of around 2.2 volts. Let's consider we have selected a Zener diode having Zener voltage of around 6.2 volts. Let's calculate the value of R2 with this formula. So R2 will be around 124 ohms. If you check the datasheet of the Zener diode, the minimum Zener current needed would be around 1 mA. But for safe side, we will consider 10 mA. So R3 can be calculated with this formula. So R3 is 620 ohms. The Q1 which we are using should be powerful enough to handle the load current and power dissipation. So ICE of Q1 should be greater than 50 mA. Now the power dissipation of this circuit can be calculated as voltage drop across the component and current flowing through it. So power dissipation across R3 will be around 68 mW. Power dissipation across R2 will be around 0.3 watts. Oh, that's too much, but we have to pay the price. And power dissipation across the transistor will be around 230 mW. Well, we need to select a transistor which can handle this much power. Let's see the simulation. This is our circuit diagram. This is the Q1, a general purpose op-amp, Zener diode, R1, R2 and R3. All values are based on the earlier calculations. Now we will simulate this. As we can see, the output current is nearly 50 mA. If we change the input voltage from 14 to 18 volts, still the output current remains the same. Now, if we add one more LED in series, which means if we change the load, still the current remains 50 mA. Well, that's how we can design a constant current regulator using an op-amp, transistor and a Zener diode. There are some advantages of this circuit. This circuit gives very stable current regulation despite changes in junction or ambient temperature. This circuit has very low power dissipation. Although there are some disadvantages as well. This topology uses many components, so overall BOM cost increases in this circuit. And due to the limitation of the discrete components which we are using, We can't use this for higher current applications. So, that's all about this current regulator. I hope you got something from this. If you haven't, you can watch the video again. Still, if you don't, you can ask your doubts in the comment box below. Hit the like button if you like this video, subscribe to my channel, and finally, thanks for watching.